Okay, we're now going to continue and perform an example of nesting the model output of the NEPD grid. I'm just going to load it again. Of the NEPD 10 grid onto a smaller grid. In this case, let's say that we go from the 10 kilometer NEPD grid. We're going to nest into a 3 kilometer grid around the San Diego Bay Area. So to do that, let's open a little tutorial here. It's called main 3D nesting. And so here at the beginning of the tutorial, there are two options. Do interpolation equal 1. This will just automate the process of nesting. And then there is also do study equal 0. So at first, I like to perform a study of whether the nested configuration is actually going to work. Then once I'm relatively confident that it's going to work, then I leave this option equals to 1, and at the end of this script here, there's the automated component that will do everything. Okay, which is very short actually. So let's start with this study. Okay, the first thing that I'm going to do is I'm going to load a particular output, and in this case the one I would recommend is this 10 kilometer output, and I'm going to start by loading, for example, in this case the July of 2002, just to get an idea of how the nesting of a variable would work. So I start by doing that. I just paste this in my MATLAB window, and so the output is there. And now I'm going to try to nest, for example, the temperature variable just to see how it looks like. So here, as the destination grid, I'm going to use SCOOS1, which is the 3 kilometer resolution grid. So I'm going to load it, and just to show it to you, I'm going to plot this grid real quick. H, comma, GRD, comma. This is just some plotting. And so this is the 3 kilometer SCOOS grid. Okay, very well. Now to do this nesting, I really want to basically interpolate a variable which is on this volume of the NEPD 10 grid to the volume of the SCOOS grid. Now to do that, I'm going to use a three-dimensional objective map. Now without going too much in the detail of the objective map, the first thing that I typically do is I build something that is called a P-map. The P-map is basically a map that for each point in the parent grid, in the child grid, it will find a certain number of neighboring points, in this case 15, of the child grid that will be used in both horizontal and vertical to perform a mapping of the volume. These P-maps are expensive to compute at first, but once they are computed, they can be saved and then used later for every, in the automated process. So for example, I already computed these. It took about 45 seconds. And so in this case, because they're already in this directory, if I paste this, it just loads them automatically. But you may want to try and rebuild them. So at this point, with this P-map and everything, and with this P-map computed, I can perform this OA3D, and the inputs are the longitude, the latitude, the depth, and the temperature field, the three-dimensional temperature field of the original grid, of the parent grid, and then I give the longitude, latitude, depths of the child grid where I want to interpolate to. A and B are the decorrelation lengths in the horizontal, and P-map is this particular map. Now in the vertical, I don't do an objective map, but I just do a linear interpolation, or actually cubic interpolation. So let's just execute this, and you see that it's actually pretty quick with this thing. It only takes about a second to just interpolate one field. So that's very good. Before going forward though, I want to perform a study of how well I would expect the nested solution to look like. And in particular, I'm going to plot a difference of the topographies and volumes of the two grids. So this is now a difference between the topography of the parent and the child grid. And where this difference is negative, this means that the child grid is actually deeper than the parent grid. So this would be an example in which the objective mapping has to extrapolate in the vertical, or the linear interpolation has to extrapolate in the vertical, because you know, the destination volume, the one of the child, is actually deeper. These areas here are instead areas where the coastline of the parent grid doesn't quite reach you know, the one of the child, and that's not a big deal, because the objective map will take care of this kind of extrapolation. So let's look, in fact, how good or bad is our extrapolation. So right now what I'm going to do is I'm going to plot a vertical section. Okay, oops, sorry. Let me just close this. I want to actually to keep this thing here to show you where I'm going to put the vertical section. So I'm going to take a vertical section now along here and plot the temperature obtained with this two-dimensional mapping, and compare it to the one from the original nested grid. So I'm going to close this, and to use that I'm going to use this function RNT section, where I pass x and y, which are the points delining the segment of the transect. So let's see how it looks. And so you can see that this is the parent grid up here that doesn't extend all the way to the coast, and this is the child grid here, which extends more. So the objective map has extrapolated here over the coast. Probably it didn't extrapolate much in the vertical, because, as we said, the topographies are quite similar. So this is a good example. You know, the topography works out well. We can also look at the surface temperature from this array, which is this next part. And so here, this is the large scale temperature. This is the region of the nested grid, and this is the temperature in the nested grid. And I don't know if it's reasonable. You know, we can check, but here you see the SST gradients are quite small. They're order 0.2. So you know, this is something that needs to be checked. Okay, so once you are confident that the nested variable is doing an okay job, then you can automate the process. So here, for example, now I want to create, you know, I chose, you know, the month of July 2002, and I'm going to now extract, for example, boundary condition and initial condition in a period that goes, say, from June to August. So I'm going to say that my index range here is going to be equal to this stuff over here. So I'm going to put it there. I already loaded the destination grid. Here I would be loading the PMAP and PMAP psi, but these are things that, if we go further up, we had computed before this example and saved in these MATLAB files. So that's why we're just loading them. And then here at this point, what I do is I just, you know, execute from erec equals all the various ranges of records that I want. It's just going to extract, you know, this nested solution. So I'm just going to put there here and just let it go, and let's see if it does it. So it's computing, so it's doing the temperature, the salinity. Now it's rotating the velocity of the parent grid, interpolating on the child grid, and then rotating back, you know, to the child grid. And so now it's saving the first nested you know, file that has, in this case, June June 1st of 2002. Now it's doing the second record, which should be July, and it should just continue, I think, for 3 records. This is July 1st of 2002, and the last one. As you can see, it's getting pretty old, pretty late here. It's 1 a.m. Should be going to bed. Okay, so this is, at this point, should be done. If I do an ls, I see that it created, for each of these shots, it created a basically initial condition. Okay, so now, since you know, probably I don't want to use all of them for initial condition, I can create a boundary condition file from these snapshots that I extracted, and this is what this part of code does. So I'm just gonna paste it here. And so now it's creating the boundary condition file, and then it's basically filling it up with those with the variables using these nested files that we just did. I think this worked. So let's see, index 1 of 3, 1 of 3, 1, 2, 3. So yeah, so it worked out well. So now I have also here the boundary condition file that I can use with the ROMS model. So that's very nice. And if I look at CTLI here, I have the 3 nested files that I just extracted. I can, for example, decide to load the velocity field, which is always scary sometimes. So let's load, for example, I don't know, the July one, and let's put the V here. So I'm loading this, and let's plot a section using sect x v, and I'm going to plot a section along the southern boundary and see how it looks, if it looks reasonable. And this is the velocity profile. So you have a negative flow here at the surface, which means that it's coming towards the south. Sorry, that it's going towards the coming versus the south. And then here you have an undercurrent flow here that is going in the other direction. So this is in July, and in July, as we know, we have a strong upwelling. The jet is very strong, so it may be reasonable. Okay, so this is an example of automation of a nesting. So if you have a particular grid that you want to check, you could probably do it. It would be fun to try one of those high. Of course, we cannot try the 1 kilometer grid, because going from 10 to 1 kilometer would be asking too much. So you'll probably need an intermediate level of nesting, but you can generate the solutions and the nesting from this outer grid, and then you can take it from there. So I hope this is going to help you. Okay. As I said, you know, if you want to call me and we can chat over the phone, perhaps I can help you more. But this, as a first step, it may be helpful for you to get an idea of how I can provide you with some help. One last thing: when I load the outputs using this command here, okay. So this was when I was loading the output. You have a lot of information. CTL .file, for example, tells you where all these output files are stored if you really want to get them, but this is probably, you don't never need it. But more convenient is this CTLF. This CTLF basically contains a map of all the forcing files that were used. So for example, if I do CTL wins, CTLF wins, for example, it tells you that the wins that were used to force this run are contained in this particular file here. And for example, if you want to load, and you can load any of the wins here. For example, if you want to load SUSTR RNT load var, you can give the CTL, you can put any record you want, say record number 600, and then you want to load, for example, the SV STR, and so here again you can load the the wins, for example, and you can plot them as we've been doing so far. In this case, this would be the wins of the parent grid, which was GRDN. So you can plot this, and so these are the wins, and you can see that they're large scale and coarse, but you can see the typical structure in the California current with these bull eyes. So anyway, and again, with that, you have also the buoyancy fluxes, and in this case our climatology and the time-dependent SST. So you have all this information, and for example, if you wanted to use the high-resolution winds from the RSM model, you can load that output, which is this one, and it will tell you then in the CTLF winds, you see that this is the file that has the high resolution RSM winds. So there's a lot of information here, and so maybe if we chat over the phone, it would be easier to convey what you need. Okay, good luck. It's a hard problem to model San Diego Bay, so but you guys are probably well armed with all your tools. Okay, ciao mente.